Hello and welcome. This is AQA GCSE Physics. This is Unit 3 called the Particle Model of Matter. We're going to start off by looking at density. Density of materials. Density is the mass of a substance in a given volume. It also relates to the arrangement of atoms or molecules in a substance in different states of matter. So here we have solid, liquid and gas. These are the particles in those three substances. And we can see that the solids are most dense. The atoms or molecules are much closer together than they are in liquids and gases. There are more atoms or molecules in a fixed volume than liquids or gases. So the most dense are the solids and the least dense are the gases. Here is the equation. This will be given to you on the equation sheet in your exam. Density is equal to mass over volume. Mass is measured in kilograms, volumes should be in meters cubed, and density in kilograms per meter cubed. However, these are the symbols that you might see in the exam. That funny letter at the beginning there is not a P, it's the Greek letter rho, and it stands for density. Useful conversions. These have been useful in past papers, and in fact our conversions are very useful for all of your science papers. Going from grams to kilograms, we divide by 1,000, and a less common one but was tested before is the idea of centimeter cubed to meter cubed. We divide by 1,000,000. So let's take a look at required practical number 5. It says use appropriate apparatus to make and record the measurements needed to determine the densities of regular and irregular solid objects. So to start off with a regular object, something like a cube, we'd start off by measuring the mass using a balance. Here's our balance and here's our regular object. We would put the object on the balance and record the mass. In this case, an example is 68 grams. We would use a formula to measure the volume of the cube, that is length times width times height. So we would measure the length, the height and the width with a ruler, and for example if we had 2 times 2 times 2, that would give us a volume of 8 centimeters cubed. We would substitute those values into the equation. That would give us density is 68 divided by 8. The answer for that is 8.5, and in this case we haven't changed the units, it's grams per centimeters cubed. However, if we needed to convert to kilograms per meter cubed, 68 grams, if we divide by 1,000 to get kilograms, is 0.068 kilograms, and the volume we divide by 1,000,000 to get 0.000008 meters cubed. We can then substitute into the equation again, and now we would get 8,500 kilograms per meter cubed. Next, we take a look at if we had to find the density of an irregular object. The volume cannot be measured with a simple equation, but when it's immersed in water, it will displace its own volume of water. That means we can measure the mass using a balance as we did before. This would give us the volume. We would fill a displacement or a eureka can until the water is level with the spout. So here is a diagram of the eureka can or the displacement can, and you can see that the water is level with the spout. We would place the object into the water gently and collect the displaced water. There goes the object. Water level rises, it gets displaced and then falls into the container. We would use a measuring cylinder to measure the volume of the displaced water. We would measure it at eye level, so remember to measure the volume at eye level, otherwise you'll get a random error. The volume of the object is equal to the volume of displaced water. So for example, if the mass was 75 grams and the volume that was displaced was 15 centimeters cubed, the density would be 75 divided by 15, which is equal to 5 grams per centimeter cubed. So we're using grams and centimeters cubed from the equation or from the question. However, we could convert to kilograms per meter cubed by dividing the mass by 1,000 to get kilograms, and dividing the volume by 1,000,000 to get meters cubed. That would give us 0.075 divided by 0.000015, and that's an answer of 5,000 kilograms per meter cubed. You may want a little shortcut here. That would convert directly to kilograms per meter cubed. That's an easier way to do it if you wish to try it like that. Next, we take a look at changes of state and internal energy. Changes of state. Changes of state are physical and not chemical changes. The substance recovers its original properties if the change of state is reversed. Let's take a look. Here is a scale going from cold to warm. We have gas, liquid, and solid. And going from solid to liquid, this would be melting. Going from liquid to gas would be boiling. And then we have going straight from solid to gas. Not many substances do that, but when they do, that's called sublimating. The process is sublimation. If we're going from gas to liquid, this is condensing, and liquid to solid, this is freezing. Remember, mass is conserved when changing state. In other words, for example, 10 grams of a solid will produce 10 grams of a liquid when melted. Next, we take a look at internal energy. Internal energy is the energy stored by particles in a system. In physics, a system means an object. Internal energy is made up of kinetic energy plus potential energy of the particles. So what happens when we heat an object or heat a system? Heating changes the energy stored in a system by increasing the energy of the particles in the system. Heating will either raise the temperature, or it will produce a change of state. No temperature rise, but there is an increase in internal energy. Let's take a look at that on a graph. Here is a graph of a substance melting and then boiling. Boiling at the top part there, and the melting is the bottom flat part there. Heating will raise the temperature in the parts of the graph that are rising, and heating changes state in the parts of the graph that are flat. So melting and boiling are changing states, and heating during that time will cause the melting or the boiling. Remember that during changes of state, there is no temperature change, just the change of state. Cooling changes the energy stored in a system by decreasing the energy of the particles in the system. So here's our graph again. This time a substance is being cooled. We have condensing and freezing at those points there. And cooling will either lower the temperature, that's where cooling lowers the temperature on the graph, or produce a change of state. No temperature fall, but there is a decrease in internal energy. So the flat parts of the curve there, the cooling causes a change of state, but not a change of temperature. So, worth going over that again if you need to. However, the next thing we need to look at is something called latent heat. The energy needed for a substance to change state is called latent heat. There is a slightly more detailed definition that we need to know. The specific latent heat is the amount of energy required to change the state of 1 kilogram of a substance with no change in temperature. That's a definition you should know and remember and should be able to answer if asked in the exam. However, there are two more details we need to know about this. And they are 1. Specific latent heat diffusion. This is the change of state from solid to liquid, in other words melting. And specific latent heat of vaporisation. This is the change of state from liquid to vapour. This is to do with boiling. So again, if we looked at our graph as we have done before, we have boiling at the top there and melting at the bottom flat part. And number 1 from the sentence above relates to specific latent heat diffusion, and part 2 relates to specific latent heat of vaporization. Next, we take a look at the equation. Specific latent heat equation, this is energy for a change of state equals mass times specific latent heat. It doesn't matter if it's melting or boiling, but this is the equation. Energy for a change is measured in joules, mass in kilograms, and specific latent heat in joules per kilogram. And these are the symbols for the equation. So here's an example. A beaker of water is heated and the energy transferred to it is measured. The initial mass of the beaker and the water is 0.160 kilograms. The final mass is 0.142 kilograms. The energy transferred as the water boiled is 50,400 joules. So the mass loss is 0.160 minus 0.142. That gives us a mass loss of 0.018 kilograms. If we put that into our equation, we have latent heat equals 0.018 divided by 400, and that gives an answer of 2,800,000 joules per kilogram. So that's an example. Next, we take a look at the particle model and pressure. Particle motion in gases. Molecules in a gas move constantly and randomly, and by that we mean they have different speeds and different directions. The temperature of a gas is linked to the average kinetic energy of the molecules. The molecules in a gas at high temperature have a high average kinetic energy. In addition, a gas exerts pressure when molecules collide with the walls of a container. Here is a container. Here are some molecules of the gas inside that container, and they collide with the sides of the container and exert a pressure. Heating a gas increases kinetic energy of the molecules. So here's a higher temperature. The molecules will collide more often with the walls, which causes a higher pressure. We can see there that the higher temperature causes more kinetic energy and therefore more frequent collisions, and that will lead to higher pressure. So we can summarize that. We've got low temperature and high temperature, and here are three diagrams to represent that. And pressure increases with increasing temperature. The higher the temperature, the higher the pressure, as long as the volume of that container stays the same. So that's it. AQA GCSE Physics Unit 3, the particle model of matter. Thank you for watching, and I'll see you soon.